Good morning, everyone. So we are now done trigonometry, congratulations. And for the next 3 units, we're going to be moving on to quadratics. And quadratics is just one of many different types of non-linear relationships. So for the next couple of days, what I'm going to do is I'm going to be making a lot of parallels to what you learned in grade 9. In grade 9, you spent a lot of time on linear relationships, relationships that form a straight line. And we used some of that back in units 1, 2, and 3, as you recall. So what I'm going to do is I'm going to try to draw some parallels between quadratics, nonlinear relations, and what you did last year to sort of compare and contrast some of the differences. So today's lesson, sort of an intro lesson, I'm just going to go on about some linear things, some non-linear things, just sort of set the stage, and then we'll get into it more with 4.2. So first of all, relations. When we're talking about relations, we're talking about a relationship between two pieces of data. And we quite often see that relationship in the form of an ordered pair, or we see it on a t-table. When x is 0, y is 2. When x is 1, y is 4. When x is 2, y is 6. And we have this relationship between x and y. Sometimes these relationships are linear. So if they're linear, x-axis here, y-axis here. If they're linear, it means that each of these points form a straight line. In quadratics, we're going to be looking at relationships that form a parabola. So we have a whole bunch of points here. There is a relationship between them, but when we connect them, you see that it doesn't form a straight line. It forms this U or B shaped pattern. So that's what we're going to be focusing on. Now, just going back to graphs, remember the x-axis is your independent variable, and your y is your dependent. So y depends on x. The number of ice cream cones sold depends on the temperature. And so our independent variable is the one that we can control, or it's the one that we are not measuring. Dependent is the one that we are measuring during the collection of this data. Now, another way to determine, so we can see right here that we have a linear relationship. It's quite easy to see when we graph it. But if we're not graphing it, if you recall last year, we used something called first differences. And first differences allowed us to see if a relationship was linear without actually graphing it. So on a t-table, we have our independent variable, and we have a set of dependent variables. And these all create ordered pairs. And if we were to graph this, this would be linear. It would form a straight line. However, without actually graphing it, can we determine just by looking at the t-table? And the answer is yes. We look at first differences. So here are first differences. From 0 to 2, we have 2. From 2 to 4, a difference of 2. From 4 to 6, a difference of 2. From 6 to 8, a difference of 2 as well. And if all our first differences are the same, that tells us that if we were to graph it, it would be a straight line. It would be linear. And so we're just looking at the differences along the y-axis. We do have to pay attention to the x-axis, though, even though it's not part of our calculations. But if I had something like this, it would appear that we have a first difference of 4, and you would say, well, that's not linear, it's not the same. But of course, we can see here by paying attention to our our X column, that we are missing a data point. There should be another data point in here. And of course, that would make everything linear. So while we're calculating first differences along the y side of the t-table, we do have to pay attention to the x side just to make sure that it's going up by equal increments. So those are first differences, and they let us know that something is linear or not. We are going to be looking at second differences. And second differences will tell us if something is quadratic or not. So for example here, if I set up a new t-table, 0, 1, 2, 3, 4, and on the y side 2, 3, 6, 11, 18. Is this linear or not? Let's calculate first differences. We have a difference of 1, we have a difference of 3, we have a difference of 5, we have a difference of 7. Our first differences are the same, so this is not linear. But if we go one step further and we calculate second differences, the difference between here is 2. Difference here is 2. The difference here is 2. Because our second differences are all the same, this tells us, so first differences, this told us this was nonlinear, not a straight line. Because our second differences are all the same, this tells us that we have a quadratic. Now, what is a quadratic or a nonlinear relation? So, quadratic, it's a non-linear, so it won't form a straight line, but it is a relationship. There is a relationship there. Sometimes we don't have any relationship. In this case, we do have a relationship. And this is when the relationship does not follow a straight line. So, some real life examples. We could have here time and distance, and I'm timing a race car starting a race. So initially it is still here, and at 0 seconds it's gone 0 distance. And I can plot this car as it takes off. We can quite clearly see that there is a relationship here. It's not linear, but there is a pattern or relationship. And we can see that this line, if we were to break it into sections, is getting steeper and steeper and steeper. So in this case, the car is going slow, faster, 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 faster. And especially between, say, this point and this point, we have very little time elapse, but it's gone a huge distance. That tells us it's going very fast. Big distance in a little time. Down here where the car is starting off, it goes a big distance, or sorry, in a lot of time, it only goes a little distance. That tells us it's going slower. And in this case, because the line is getting steeper and steeper and steeper, it tells us that that car is accelerating. Over the last 6 weeks, you've seen a lot of quadratic relationships on the news. So we have time measured usually in days, and we have number of COVID cases. And we started off with a case a day, and then 2, and eventually we've got something like this. So there is a relationship between the number of COVID cases in Canada or Ontario each day and the time, say, in days. The relationship you can clearly see, but it's not a linear relationship. It's not following a straight line. We're not adding the same number of cases each day. In fact, the rate of growth was slow back here in early March. And in April, almost going into May, it's quite a bit higher. One of the things that we're trying to do is flatten the curve. And so This line here represents the number of hospital beds. And we know people are going to get corona, but we can't, if we only have X number of hospital beds, just making up a number here, 500 in an area, we can't have 1,000 people getting corona serious enough that they need a hospital bed. Obviously, all these people here don't get a bed. So what we've been trying to do by social isolating is taking this linear relationship, but spreading it out. So people are still going to get coronavirus, we know that. But if we can keep the daily gains and the number of people who need a bed under our limit, then we're going to be able to treat those people. So looking at it again, this is definitely a quadratic relationship, and you'll see this more as we move in. We want a quadratic relationship that looks like this. This here is a parabola shape. We're trying to keep it underneath rather than everybody getting it all at once and having this group of people that we cannot treat. So same number of people are getting it. However, we are flattening that curve out. We are spreading it out so it stays below a certain level so that we can treat those people. So both of these are quadratic relationships, and we'll be looking at those in days to come. So once again, another example here. Let's say two parachutists jump out of a plane at 2,000 meters. And these tables here record their time and their height. So we can change X and Y to other letters. And so here's the first parachutist. So at 0 seconds, 2 seconds, 4 seconds, 6 seconds, and 8 seconds, we are going to take measurements of the height this parachutist is at. So when the first parachutist is ready to jump out at 0 seconds, they are 2,000 meters in the sky. So this is time in seconds, this is height in meters. After 2 seconds, they are at 1980, 1960, 1940, 1920, and after 10 seconds at 1900. Is their fall linear or non-linear? So if we look at our first difference here, we can see that in 2 seconds, this person drops 20 meters. We have another drop of 20 meters. We have another drop of 20 meters, another drop of 20 meters, and another drop of 20 meters. It appears that if we were to graph this, this would be a linear descent. And a quick check over here on our X side, we can see that we're going up by the same interval, 2 seconds each time. So this tells us that this is definitely linear. If we were to graph it, we would have time, we would have height. Person starts at 2,000 and they are falling toward the ground. Not only that, we can calculate using our slope that they are falling 20 meters every 2 seconds. So our slope here is they're actually falling 10 meters a second, 10 meters in 1 second. And this negative tells us that we have a negative slope where they are falling. All right, person number 2. So we have our time in seconds, our height, 0, 2, 4, 6, 8, and 10. Starts at 2,000. After 2 seconds at 1,980 feet. Then 1920, 1820, 1680, 1500. So when we calculate our first differences, we can see we have a drop here of 20, a drop here of 60, a drop here of 100, a drop of 140, and a drop of 180. Our first differences are different, so that tells us that it's not a linear fall. Is it a quadratic fall? So we can go to our second difference, and we can see here that we have a drop of 40, a drop of 40, a drop of 40, and a drop of 40. So this tells us that our second differences are constant. Fancy math word for the same. So therefore, there is a relationship, and it is quadratic. And if we were to graph this, we have time, we have height. We are going to get a curve. And that curve is actually half of that parabola that I was talking about. So that whole quadratic relationship would look like a parabola. We'll get more into that. Sometimes part of it's missing in our data set. I know in this case it looks like the parachute has hit the ground and then jumped back up in the sky. That's not the case, but mathematically there is a second half to it. Actually, I've drawn that wrong. In this case, a quadratic would look more like this. So height, the person's falling faster and faster and faster and faster. And in this case, in negative territory, mathematically, we would have the other half of the quadratic relationship. Of course, this half in negative territory is not possible. Mathematically, it's there. It'll be part of our expression. We'll be working with that as the days roll on. But in this case, we're only dealing with this part of the quadratic relationship. So there you go, ladies and gentlemen. And in this case, if we calculate our rate of descent, we are falling 20 meters. Our second difference here is, actually, you know what? I won't confuse you with that right now. So that is that. Just hopefully a nice, easy intro to quadratics, and next day we'll start to get into it in a little bit more detail, and we'll start to learn the different parts of the parabola. So that is that. Good luck with your homework. If there's any issues, please reach out to me. I can send you solutions. Reach out to your classmates who can help work you through a particular problem one-on-one in real time, and we will see you next time.